Hello, everybody. Today, what we'll be doing is we'll be taking up Mobius 6. And I copied down the questions this time, so we have all the time we need. Perfect. So let's start. A ball is dropped from a height of 5 meters. Each time the ball bounces, it reaches half of its previous height. The ball bounces indefinitely. What is the total distance traveled? So first, what we need to realize is what this ball is doing. So in essence, what would happen is that if we're standing on some sort of platform, 5 meters above the ground, right? We would drop a ball. So this ball would travel 5 meters. Then it would bounce up and it would bounce half of its height before, and then it would bounce back down. And then it would bounce again half of its height, and the half over here. Then it would bounce back, and then up half, down, and so on and so forth. So then what we can start to see is if we actually write down what happened, so it would jump first, it would travel 5 meters, then it would travel a half of 5 meters twice. So that's why we multiply by 2. And the reason it's twice is because it goes up and then back down. And that's where this 2 comes from. So then it would travel plus a half of 5. So it would be 1/2 squared times 5 because it's a half of 5. And again, you multiply by 2 because it travels both up and down. So then plus a half of a half of a half, which would be a half cubed times 5 times 2. So what you can see, so this is actually going to become a sequence because each time you're just multiplying it by a half. So then what we can do is we can turn this into a sequence. So what first I'll do is I will factor out 5. So if I factor out 5 out of everything, what I'm going to get is 5 times 1 plus 2 times a half plus 2 times 1/2, 1/2, sorry, 1/2 squared plus 2 times 1/2 cubed. Sorry, I'm trying to figure out what I'm writing. And plus 2 times 1/2 to the 4th, and so on and so forth. Okay, so then what happens after that is so then again we can factor out the 2 from here, so it's going to be 5 times 1 plus 2 times 1/2 plus 1/2 squared plus 1/2, 1/2 cubed plus 1/2 to the 4th, and so on and so forth. And finally, we can start to see our sequence. Is just a geometric sequence where each time the ratio is 1/2. So then we can get 5 plus 5 times 1 plus 2 times sigma from n equals 1, because our first term here is a half, right? That's why n is equal to 1 to infinity, where it's 1/2 to the power of n. And now what we can do is we can solve this. So if you remember in class, we developed the formula for what happens when you go to infinity of a geometric sequence. So in a geometric sequence, right, the sum of a geometric sequence, sorry, is a times 1 minus r to the power of n plus 1 over 1 minus r. Now when r is less than 1, when you take r to the power, and n is going to infinity, if r is smaller than 1, this term is going to go to 0. So we'll end up with is a over 1 minus r. So that's how we can calculate the sum of the sequence. So our first term is a half, so we're going to have 1/2 over, our ratio is also half, so it's going to be 1 minus 1/2, which is equal to 1/2 over 1/2, which is 1. So then this is equal to 5 plus 5, sorry, 5 times 1 plus 2 times 1 is 2. So it's going to be equal to 5 times 3, which is then equal to 15. So this ball will travel 15 meters. Perfect. Let's go on to the next question. clear drawings. And let's scroll down. Okay. Which of the following geometric sequences converge with a sum larger than 1? So again, if we want to check for convergence, there's two things we can do. First, we can check if they diverge by seeing if the limit as n approaches infinity approaches 0. Because if you think about it, if you keep on adding something, so if I go 1 plus 2 plus 3 plus 4, if my term keeps becoming bigger, then obviously won't be able to go to a certain number. However, if my thing which I'm adding starts to approach 0, then what will happen, right? So plus 0.00001 and so on and so forth. What we'll see is that this is all that would matter, because everything past that will just be approaching to an addition of 0 as well. And then what we can do is we can see if, just with the previous formula that we saw, which was a over 1 minus r, we can see if that sum that it does approach is larger than 1. So let's start then. So let's take the first one. So for the first one, we have the sum of infinity when n equals to 0 of 2 minus 1 over n. So if we rewrite this, we're going to get sum from n equals 0 to infinity of, so 2 minus 1 minus n can be rewritten as 2 to the power of negative 1 plus n, which would then become 1 over 2, 1 plus n. So then we can see that as n approaches infinity, this is going to approach 0. So we do know that we know it might converge. So then we can see what it converges to. Just remember that just because it goes to 0, it doesn't necessarily mean it converges. Just remember that the example we got in class was 1 over x. But in this case, because it's a geometric series, we do know that it converges, and that's why we can continue. So 1 over 2 to the power of 1 plus n. So now, because n equals to 0, we know that our first term, sorry, I'm getting ahead of myself. So what will happen then is we have 1 plus n. And we don't really know how to work with that, right? Because then we don't have a concrete ratio. So what I'm going to do is I'm going to try to get rid of this 1. And I'm going to do that is it's going to be 1 over 2 to the power of n times 2, right? Because it's the same thing as 2n times 2 to the power of 1. And you know, so a to the power of b times a to the power of c is the same thing as a to the power of b plus c. That's what happened over here. So then what I'm going to do is I'm going to factor out this 2, or 1/2 in this case, out of the sum. So it would be 1/2 times the sum. And I should be putting the symbol of sum everywhere, but I'm just a bit lazy. But so then it would be sum n equals to 0 as n approaches infinity of 1/2 to the power of n. And now we can kind of use the formula we got before. So we know this then converges to, it's going to be equal to 1/2 times, so the first, because n starts with 0, our first term a would be 1, because 1/2 to the power of 0 is 1. So it'd be 1 over, our ratio is 1/2, 1 minus 1/2. So then this would equal to 1 over 2 times 2, which is then equal to 1. So this one would not converge to a sum larger than 1. It would just converge to 1. So then if we look at our next one, 5n minus 4n over 2n. So again, this time we need to make sure that we notice that n equals 1. So what we're going to do here is that we can actually split these up. So what do I mean by that is we can go, well, we have sum of n equals 1 to infinity of 5 to the power of n over 2 to the power of n minus 4 to the power of n over 2 to the power of n, right? So in brackets. So then we can split this up, and it will be sum of infinity n equals 1 of 5 over 2 to the power of n minus sum n equals 1 of 4 over 2 to the power of n. But what we'll see here is that our ratio actually is not smaller than 1. So in this case, our ratio is 2.5. In this case, our ratio is 2. So what we know then is that these series will not converge at all. And therefore we know that because they don't converge, the question asks if which of the following series converge with a sum larger than 1. So because the series doesn't converge, we can just say that that's wrong as well. Okay, so then we move on to this one. So here we're going to use a similar trick to the one we just used up top. So firstly, we're going to separate it into two different sums. And the reason you can think of this, right, is because a sum, just quickly, is just is a continuous addition of some terms. So if you have a sum of a plus b to the if for instance we have a sum of a plus b, right, and we're adding this from 1 to 5 times, the same thing as saying a plus b plus a plus b plus a plus b, and so on and so forth. And what you can see then is that you can group your b terms and your a terms. And so then you can see that it would just be a sum of a's plus a sum of b's. So that's how I know I can split this up. So then over here, I'm going to split it up. So we're going to get sum n equals to 0 of 3 times 2 to the power of n over 3n plus 1 minus sum of 4 over 3n plus 1. So now again, I want to get it to a geometric series. So what I'm going to do is I'm going to simplify some things. So over here, what I'm going to simplify is I'm going to simplify this 3 and this plus 1 over here, because just like in the first example, this 3n plus 1 is the same thing as 3 to the power of n times 3, and that's what I'm really simplifying. And then over here, what I'm going to do is I'm going to take out 4/3. So in the end, what it should look like is it's going to be sum of 2/3 to the power of n equals to 0, minus, and then over here, I'm going to factor out 4/3. As I said, 4/3. That's going to be sum of 1 over 3 to the power of n. And the reason I can factor this out is, again, if you can think about just a sum, right? So if we have a sum of a constant times a, so we're only really adding the a, so then it would be, if you can imagine, ca plus ca plus ca plus ca. And so that way, I know I can just factor out the c, so it would be c times the sigma of a. So that's what I'm doing here, because if you keep adding the term and you're multiplying that constant term by a constant, or you're multiplying that term by a constant, then I can just factor out that constant. So that's what I'm doing over here. So then we have our geometric series, and what we can do is we can calculate their sum of convergence then, like we did before. So then, if n equals to 0, then our first term over here is 1, and then our ratio is 2/3, so it's going to be 1 over 1 minus 2/3 minus 4/3 times, so over here our first term is 1 again because n is equal to 0. So 1/3 to the power of 0 is 1. So it's going to be 1 over 1 minus 1/3, because 1/3 is our ratio. So then we can see that over here what we're going to get is 3 minus, so 4/3 times 2. Over here we're going to get 2 because it's 4/3 times, it's going to be 3 seconds. Then we can simplify the 3's, and that's how we get 2. So 3 minus 2, and that's equal to 1. So this one also doesn't work because we have to have a sum larger than 1. Finally, we're going to get to our last example over here. So it's going to be sum to infinity n equals to 0. So again, we are going to separate our terms. So it's going to be 3n over 2 to the power of 2n times 2 to the second, just like we did before. So then what are we going to do? We're going to factor out this 2 over 2. We're going to take it out. It's going to be 1 over 4 times sigma n equals to 0, 3n over 2 to the power of 2n. So then this 2 to the power of 2n, I'm just going to rewrite it so it's easier for us to work with. It's 1/4 times sigma n equals to 0 of 3 to the power of n over 4 to the power of n, right? Because I can just do 2 to the power of 2n is equal to 2 to the power of 2 power of n. And then again, we get our first term is 1, and a ratio of 3/4. So then this is equal to 1/4 times 1 over 1 minus 3/4, which is then equal to 1/4 times 4, which is then equal to 1. So again, none of these work, and the thing I would pick is none of the above. Hopefully that makes sense. So let's move on to the next question. Which of the following are true statements? So if an exists, then an approaches 0, and that is true. And that's, as we discussed before, if your series converges, then you know that your term of the that you're adding consistently has to approach 0. Because if you're not consistently adding 0, then your thing's going to become bigger and bigger and therefore can't converge. So this one would be true. If an converges, then 1 over an diverges to infinity. And this is false because it doesn't necessarily diverge to infinity. It can also diverge to negative infinity. So the reason you may think this is true is because if an converges, that means that an, as n approaches infinity, approaches 0. So that would mean that sigma 1 over 0, that approaches infinity. And by that logic, you can think, well, then, because I know that my an term is not approaching 0, that means it's getting bigger and bigger, and that means it diverges. But again, the only flaw you would have then is that this can diverge to negative infinity. And that's the problem. That's why that one wouldn't be true. So then if an to the approaches 0, then sigma of an converges. And so this is false. And the example we got in class, the most clear one, is 1 over x. So even though 1 over x does approach 0, or 1 over n, you can say. So sigma n equals to 0 to infinity, 1 over n. Even though this term does approach 0, the overall sequence doesn't actually converge. So 1 over 1 plus 1 over 2 plus 1 over 3 over 4 does not converge. And so that's kind of the best example to show. Okay, so if the partial sum is smaller or equal to 170 for all n, then sigma an converges. So this is false because you may think that this means that it does converge, because what is partial sum? Partial sum is basically an plus an minus 1 plus an minus 2, and so on and so forth. Or a better way to visualize it, of course, is it's just a1 plus a2 plus a3 plus a4, so on till an. And you can think that, well, since it's always going to be, the absolute value of this is always going to be smaller than 170 for all n, then an converges. So, sorry, I'm moving this. So then this would actually be, this would actually be, this would be false. And the reason it would be false is because you can also have an oscillating, something that oscillates, and that means that it doesn't converge. So, for instance, if you remember cosine, it doesn't converge just in the regular terms of converging, because it goes to 1 and then -1 and then 1 and -1 and then 1 and -1. So the same thing can happen to Sn, where, for instance, even though it's always smaller than 170, it could go 170, 160, 170, 160, and then it still doesn't converge. So even though the partial sum is always going to be smaller than 170, that doesn't mean it converges to one singular number. That's why that one would be false. Okay. Oh, sure. So then let's go to the next question. Oh, see, in here I put none of the above as well. Which of the following statements are true? Select all true statements. So if f prime of x is bigger than 0 for x is smaller than a, and f double prime at x is bigger than 0 for x is greater than a, then f must have an inflection point at afa. Now, this is false. And the reason it's false is because f double prime at x is bigger than 0 means that this is concave upwards. So it's concave upwards over here for x smaller than a, then f double prime at x for x greater than a, that means it's also concave up on the other side. So if it's concave up on both sides, then that means f at A, if you connect them, there's no way that this would be an inflection point. This isn't an inflection point. On the other hand, if f at x over here was smaller than 0, right, then that means it would be concave downwards at that point. So then that would be concave downwards like this. And so then this would be an inflection point because at this point, you go from being concave down to concave up. Okay, if f double prime at A is equal to 0, then f has an inflection point at A, fa. Now this is wrong because what you can think of is you can think of your x to the power of 4 function. So your x to the power of 4 function looks like this. And so what you'll find is that f double prime at A does equal to 0. So f double prime at 0 equals to 0. And we can check this. So f single prime x is equal to 4x cubed. So then you're gonna have a critical point at 0, and that's where your maximum is gonna be. But then f double prime at x is equal to 12x squared. But then what we see is that even though again you have a critical point at 0, that critical point isn't an inflection point. In this case, it's just a minimum. And that's why not every time you have a critical point in your second derivative do you get an inflection point. Okay, if f has an inflection point at AFA, then f double prime at A equals to 0. Now, that's not true. And the best way to think of this one is the cube root function. So in the cube root function, your function looks something like this. Draw that a bit better, like this. And so over here, you get an inflection point because it goes from being concave up to concave downwards. But over here, what you'll get is an infinite slope point. So it's going to be like this. So in that place, your second derivative just won't exist. But that's what will indicate an inflection point in that case. So just remember that an inflection point can either be by a point that does not exist or that, as we see here, equals to 0. Just like in the first derivative, you can have a maximum not only if your point, not only if you have, what is it called? Not only if you have a critical point. Anyway, a critical point is when something's equal to 0 or doesn't exist. That's what I was trying to say. F cannot satisfy both f double prime at x is smaller than 0 and limit as x approaches infinity at fx is equal to 0. It can satisfy both of these because all this states is that this basically states that you can't be concave up. So this means that you're concave downwards and that you are approaching 0. But as x approaches infinity. But this is true because, for instance, if you have a function like this, and as you see, as x approaches infinity, you're approaching 0, but you are concave downwards. So in our actual function, as x approaches infinity, f of x approaches 0, and we are concave downwards. So that's why that one isn't true. Okay, let's continue. Okay, I think I have that Sn one. I added it at the end. Did I not? Oops. Okay, I missed one. Over here, it says also one with Sn and diff additions. So I believe that question, it looked something like this. I don't quite have it with me, but it was basically saying, like, let's say that your Sn, your partial sum, your Sn is equal to 4n over n plus 2, okay? So then your sum looks like n equals to 0 to infinity an. And then what you need to calculate is you need to calculate the sum, for instance, from n equals to 12 to 16 an. So what you need to realize then here is that your Sn, so S at 1 is equal an. S at 1 is equal to A1. S at 2 is equal to A1 plus A2. S at 3 is equal to A1 plus A2 plus A3. So then, if you have S16, sorry, I'm going to approach this a bit differently. So then what you can realize is that if you want to get the addition from 12 to 16, what you need to do is you need to go A12 plus A13 plus a14 plus a15 plus a16. And that would equal to s at 16, or the partial sum at 16. So then what you can do is, this is Sn. So at S16, if you want to calculate the sum of all first A16, S at 16, that would equal to A16 plus A15 plus A14, and so on and so forth till A1. Well, we only want to get it from A12 to A16. So then what we can do is we can do S16 minus S at 11, because S at 11 would be A at 11 plus A at 10 plus A at 9. And so by doing that, you would eliminate everything over here, which is after 12. And that way you would only get A12 to A16. So then in essence, what you would do is you would just go 4 times 16 over 16 plus 2 minus 4 times 11 over 11 plus 2. And that would give you, so you're basically doing your partial sum up to 16 minus your partial up to 11. And you would get then your answer of your addition from 12 to 16. Okay, which of the following series are divergent according to the test for divergence? So over here, what we need to do is the divergent according to the test of divergence. So the test of divergence is what we discussed in the beginning, where you see if your an is approaching 0 as n approaches infinity. And if it doesn't approach 0, so if an does not approach 0 as n approaches infinity, then you know for sure that your series is divergent. So if like an approaches 5, then you know it's divergent. But as a quick aside, as I mentioned, you can't say that a series is convergent just because an approaches 0. So that's kind of your first criteria to check. So if an doesn't approach 0, you know it's divergent. But if it does approach 0, you still have to do other tests to make sure that it is convergent. Okay, so then let's go one by one and see. So over here, what do we have here? Over here, we have series as n equals to 1 to infinity. And so what we can see is that this is going to become, so we can factor out 5 cubed and 7 squared out of it. So it would become 5 cubed over 7 squared times sigma, and then because it's negative n, your 7 and your 5 would flip, so we get 7 over 5 power of n. So 7 to the 5 over to the power of n, as n approaches infinity, this is not going to approach 0. All this term is not going to approach 0. It's not going to approach 0. And so you know that this sequence is divergent, in fact. Okay, so then we go here, and here you can just see, so you can kind of go like limit as n approaches infinity, negative 1 over n sigma root of n. And so this one does approach 0. If you plug it in, you'll get that this approaches 0. Therefore, this it's not divergent according to the test for divergence. You can kind of see that it's approaching 0 because you have infinity on the bottom. But in the very practical sense, what you're going to need to do is you're going to have to use the squeeze theorem by saying, like if you needed to show this on a test, for instance, you would say negative 1 to the power of n. You know it's going to be smaller than 1. It's going to be smaller equal to 1, but bigger equal to negative 1. And then you'll just use your squeeze theory to actually prove that it's converging, that the limit is 0 as n approaches infinity. So negative 1 over n root of n, smaller equal to negative 1 to the power of n over n root n, smaller than 1 over n root n. And then you know that these two approaches 0 as n approaches infinity, and so the one in the middle just has to be that. Perfect. Let's look at this one. So arctan 1 over n. So arctan of 1 over n. So this one, what you see is that 1 over infinity is 0. And so arctan at 0. So if you take the limit, 1 over 0, 1 over infinity is 0. So arctan at 0 is actually equal to 0. So this term approaches 0 as n approaches infinity. And so therefore, you don't know if it's divergent right away with this divergent test. Then 1 over root n as n approaches infinity. 1 over n approaches to 0, and so this one you don't know for sure if it's divergent, just from the test for divergence. Although, you can kind of figure out that this is in fact divergent, but you don't put it down, because here we're asking you for, according to the test for divergence, but here what you can think of is if you know that 1 over n diverges, and over here you have 1 to the power of n to the power of 1/2, which is all the terms here are smaller than 1 over n. So then for sure you know that 1 over n to the power of half also diverges, since all the terms, because it like reaches, it climbs even slower than here. Yeah, so you know that this one would diverge as well, logically speaking. That's not a rigorous proof I just provided you. I just can't figure out the rigorous proof right away. Okay, let h at t be the height of water at time t in a container that is being filled by water from the top at a constant rate. This question is concerned with the properties of the graph h at t when the container has different shapes. Which of the following statements are true? So here what you can kind of do is you can go for each one and you can try to draw a picture. So if the container is a sphere, so sphere, if you can think about it, you can just draw a circle and you can think of how a circle fills up. So h is concave downwards for all t. So if I were filling this sphere up, then in the beginning, it would fill up a lot faster, right? Because you have less, like the surface, the amount of things you need to fill up here is like the container itself is smaller down here. So this part would fill up a lot faster. Then in the middle, it would start to slow down because each like layer that you need to fill up you need to fill up more. And then it would start filling up faster again. So that means that at first it would fill up quickly. So if you can think like it would speed up. So if it starts like at 0, it would speed up, and then it would slow down, and then it would speed up again. And so here we see that in actuality, it would be concave up, speeding up, then it would slow down, and then it would speed up again. So we see is that it's not concave downwards all the time, it would actually change. So if it was concave downwards all the time, then it would need to start real fast and then slow down, right? Okay, if the container is a sphere, h has a point of inflection. So just as we saw, because it fills up quickly, so it starts filling up quickly and then it slows down. It starts filling up quickly and then it slows down, and then from the slowing down it goes back up. So this is a poor picture. This would be a better one for here. So as we see, it fills up quickly and then it slows down and then it speeds up again. Right over here, we would get a point of inflection. So this one is true. The container is cylindrical ht. H prime at t is constant for all t. So if our thing is cylindrical, what you can kind of think of as a rectangle. And at a rectangle, each layer is the same. So that means it would fill up at a constant rate. So a constant rate would look something like a line. And so then the derivative of a line is just a constant. And so therefore this is true. The container is a cone. The tip down, h prime at t, is constant. So if it's a container with a cone with the tip down, you can kind of see it as a triangle. So at the bottom, then it would fill up a lot quicker. And as it rose up, it would start to fill up more slowly because each layer would kind of be a bit bigger. So then what you would see is that it would start filling up quickly and then it would slow down. And so then you would know that the first derivative of this, the graph of this, would not be a constant. It would more so be a line. Okay, and that's it. Let's go to the next one. And here we have our two hardest questions of this movies. Okay, so let f of x equals to ln x plus 4. That's our function. And suppose we approximate f using the Taylor polynomial of order n equals 4 about x equals -3 on this interval. So which of the following are possible values for the error in the approximation according to Taylor's inequality? So for the approximation, what we need to remember is the way we want to approximate our error is as follows. So it's going to be f to the nth plus 1 derivative, f to the nth plus 1 derivative of x times x minus x null to the power of n plus 1 over n plus 1 factorial. And so all of these are absolute values. So all of this is basically absolute valued, and you can think of every term as absolute valued as well. Okay, and so this is how you can find your error for how far away your Taylor polynomial would be from your actual function. So then what I'm going to begin doing is sometimes you'll see that this is referred to as k. And so what I'm going to begin with is I'm going to find our k. So then what is our k? So what we need to figure out, if we want to figure out what our k is we need to think about our derivatives. How do our derivatives look? So then why don't we just start playing around and see how the derivatives of ln x plus 4 look like. So then the first derivative, f prime at x, is equal to x plus 4 to the power of -1, or 1 over x plus 4. Then f double prime at x is equal to negative x plus 4 to the power of -2. Then f 3 prime at x is equal to 2 times x plus 4 to the power of 3. Then f to the fourth prime is equal to 6 times x plus 4 to the power of -4. And over here I meant to say -3. And so on and so forth. And what you might notice here is that the way our derivatives look like is like this. So if we were to think of what does fn, so the nth derivative of f of x, the way it's going to look like, well, we can kind of start to see a pattern. And this should be -6. Sorry, because if you plot down the negative, you can kind of start to see a pattern. So and that pattern is that it's going to be -1 to the power of n plus 1 times n minus 1 factorial to the power times x plus 4 to the power of n, -n. So let's check this out if this generalization works. And the reason I can see that this factorial is because you see it's going to become 1 times 2. Then as you take the third one, it's going to be 1 times 2 times 3. As you take the fourth, it's going to be 1 times 2 times 3 times 4, and so on and so forth. And that's how I know it's n minus 1 factorial. Again, this is 1. This is the second. This is the third. So at the third, we go 1 times 2. And that's how I know it's n minus 1 factorial. Then the negative, we see that every even, we're going to get a negative, and every odd one, we're going to get positive. And so this way, every time. So if this is a 1, -1 to the power of 2 is 1, so we're going to get a positive. And if n is, for instance, 2, we're going to get odd here. -1 to the power of odd is going to give you a negative. Then this is just negative n. So as you see on the fourth derivative, we're going to get to the power of -1. Perfect. So now what we need to do is we need to realize two things. So the first thing we need to realize is because we're taking the absolute value of this, then this -1 doesn't really matter. Because no matter if it's negative or positive, we're still going to get a positive because of the absolute values. So this part you can stop thinking about. Then the next thing you can think of is that for the actual equation, we're using n plus 1. So if we plug in n plus 1 over here, the actual factorial, so f at n plus 1 of x, that's going to equal to n factorial over x plus 4 to the power of -n plus 1, like that. Okay. Now, finally, what we need to think of is we need to think of how to maximize this function. And the reason we want to maximize is because we want to find the biggest possible error for something, right? Because it doesn't help us if we know that the smallest possible error we can make is 0, right? We want to know what's the biggest mistake we can make. And so that's why we need to think of a way, at what point in this interval will this k be the biggest? And so for that, we need to first think of our function. So our function is n factorial over 1 over x plus 4 to the power of n plus 1. So what we can see is that this function is actually a decreasing function. It's a decreasing function, right? As x is smaller, f of x is bigger, and as x becomes bigger, f of x becomes smaller. And so then at our range, which is -7 divided by 2, -5 divided by 2, we can see is that the biggest value we're going to get is if we, instead of x, we get -7 over 2, because that's the smaller value, So that means that we would get the biggest result if we take the smallest value. So negative 7 over 2 is what we want. And so now we figured everything out for when we plug it back into here. So our k would equal to n factorial times 1 over negative 7 over 2 plus 4 to the power of n plus 1. Cool. What I want to do quickly, I want to just shift things up. So let me shift this up. There, let's shift it up right over here. Just so we have some more working space, but what I really want to underline is we found our k right over here. Perfect. So now let's plug in our k. Let's plug in our k into the equation, and then let's see if we can find everything else. So right away, while I'm plugging in k, I can see that because we're the Taylor polynomial we're taking of order n equals 4, then the n plus 1 is going to be 5. So we know that all the n's here can be replaced with 5s. So while we're plugging it in using this formula, we can already start to figure out what's happening. So because we know our fn plus 1 derivative is going to take this form, and we already know what to plug in, so we know that we're going to get 5 factorial times 1 over negative 7 over 2 plus 4 to the power of n plus 1 is 5. Sorry, we have n factorial here, not n plus 1 factorial. So our n is equal to 4. That's my mistake. So over here it's going to be 4 factorial, not 5. But here it's going to be 5 because it's 4 plus 1. Our n is equal to 4. It's going to be 5 factorial. Then we're going to get a times x minus x null to the power of n plus 1. So our x null in this case is negative 3. X null just represents around what you're building your Taylor polynomial. And in this case, it's given to us as negative 3. So then minus negative 3 is going to be plus 3. It's going to be plus 3. And I'm just leaving my x because we're going to figure it out in a bit. Plus 3, n plus 1. So that's going to be 4 plus 1 is 5. So to the power of 5 over n plus 1 factorial. So 4 plus 1. Why did I write 5 here? I thought we already, I said it should be 4, and I wrote 5 again. It should be 4, because our n is 4. It's 4 factorial, and then on the bottom, it's going to be 5 factorial. There you go. So now, let's figure out what our x is. So just to remind you, in theory, this is also absolute value over here. And why is that important? Well, in this case, it becomes important, because it's x minus x null, the absolute value of that to the power of 5. And so what that means is that, again, we're trying to maximize our error. We're trying to see what the biggest error can be. So what we're trying to do is we're trying to maximize what's inside of these brackets. And so to make it the maximum possible value, what we want to do is we want to subtract the smaller number over here, right? Because if we subtract negative 7 over 2, we're going to get a smaller number than if we subtract negative 5 over 2. So that's why the thing we're going to replace with our x is negative 5 over 2. So the thing inside of here would be a bigger number. And so then if you take a bigger number to the power of 5, we're going to get a bigger number as well. If we put in negative 7 over 2, we're going to get a smaller number, and the smaller number to the power of 5 is going to be here. Let me write it out. What I'm trying to say is that negative 7 over 2 plus 3 to the power of 5 is smaller than negative 5 over 2 plus 3 to the power of 5. And that's why, because we want to see what the biggest error can be, we pick negative 5 over 2 plus 3. And at this point, we've got everything we need to find our error. We kind of plugged in all the numbers we need. So now all we need to do is calculate. So then what we're going to notice is that 4 factorial and 5 factorial, they can cancel out. All that's left is the 5, right? Because 5 factorial is 5 times 4 times 3 times 2. And 4 factorial is 4 times 3 times 2. So the 4 times 3 times 2 cancel out. So we can get 1/5 times, and then we see here it's over to the power of 5, and here it's to the power of 5. And this is 1 over that. So it's going to be negative 5 over 2 plus 3 over negative 7 over 2 plus 4, all to the power of 5. What we're going to find is that actually what's inside these brackets is equal to 1, and 1 to the power of 5 is 1. So we're going to get equals to 1/5. So that means that our error bound is basically 1/5. So which of the following are the possible values for the error in the approximation according to Taylor's inequality? So what we know is that our error, we're okay as long as it's smaller or equal to 1/5, right? The biggest error we can have is 1/5 away from our So the Taylor polynomial would give us something, and the biggest kind of mistake or error bound would be within 1/5 of that answer. So our actual function would be 1/5 away from what our Taylor polynomial gave us. So that means that anything equal or small to 1/5 is a go. But all of these choices over here are bigger than 1/5. So because all of these choices are bigger than 1/5, none of these are possible values for the error in the approximation according to Taylor's inequality. Okay, and finally, let's go to our last question. So for which values of n does the Taylor polynomial of order n for f of x equals to e to the power of 2x centered at x equals 0 approximate the value of the function with an error of 10 to the power of -6 on the interval -1, 0. So again, if we remember, the way we find that error bound is we try to find this. So we try to maximize f of n, the nth plus 1 derivative of x times x minus x null to the power of n plus 1 over n plus 1 factorial. And so the first thing we kind of need to do is we need to find what is the nth plus 1 derivative. So let's start taking derivatives of e to the 2x. So f prime of x is equal to e to the power of 2x times 2, right? Because we need to chain rule it. So the derivative of 2x is 2. So then the second derivative of x is going to be equal to e to the 2x. Then again, we chain it. So it's going to be times 2 times 2. In other words, e to the power of 2x times 2 to the power of 2. F prime prime. F third prime of x is going to equal to e to the power of 2x times 2 times 2 to the power of 2, which is then equal to e to the power of 2x times 2 cubed. Okay, cool. So basically the nth derivative is equal to fn. The nth derivative is equal to e to the power of 2x times 2 to the power of n, and the nth plus 1 derivative of x is equal to e to the power of 2x times 2 to the power of n plus 1. Okay, but now again, what we need to do for this is we need to maximize this. So how can you make this the biggest number possible? So what we're going to do is just give. Hello, sorry, just needed to do something. Okay, so then what's going to happen is 2 to the n. So then what we need to do is we need to try to maximize this. So the way we're going to maximize this is we need to look at an interval and see what do we need to plug in to maximize this. So if we plug in anything, like if we plug in -1, for instance, we'll get 1 over e to the power of 2, and that would make it a smaller number. So in this case, the biggest number that we can get is if we plug in 0. So then we would get e to the power of 0, which would equal to 1, and all we would be left with is 2 to the power of n plus 1, which would give us our biggest result. So that's why we are going to pick our x is equal to 0. So in essence then, to maximize our result, we would make f n plus 1 at 0, because that's our interval on the interval of -1 to 0. So to maximize that, the biggest one would be 0. And you would get just 2 to the power of n plus 1. Okay, so that's our k. That's how we maximize our k. Then we need to again deal with x minus x null n plus 1. So this time we're centered around 0. So our 0. Okay, let's just rewrite it like we did last time. So then we know that our fn plus 1 times x. So our n, in this case, that's what we're looking for. So we're going to get 2 to the power of n plus 1 times x minus 0 to the power of n plus 1. So now, again, because you need to remember that this is absolute value of x, we need to start thinking of what would maximize our result on this interval. So if we put in 0, everything is going to become 0. That's kind of going to be our smallest value. So what we see is that if we look, for instance, pick 0.5, that's going to give us a value, but it's not going to be the biggest value. The biggest value would be if we put in -1, because -1, the absolute value of -1 is 1, then we're going to get 1 to the power of n plus 1, which is just equal to 1. So then this term would kind of disappear, but it would still give us our biggest result possible over n plus 1 factorial. So then in the end, what do we get? We get that so that we get our biggest error is going to happen at 2n plus 1 over n plus 1 factorial. Now we need to figure out what order of the polynomial or what n we need to get so that the error would be within 10 to the power of negative 6. Now, what would really happen is that you would just need to plug in your 9, your 12, your 11, and your 1 and see where that whether that's in with whether that's smaller than 10 to the power of negative 6. What I usually do during this is I would just open up Desmos. So let's clear all drawings. I'm going to open up Desmos. And if we put in an equation, so 2 to the power of x plus 1, x plus 1 over x plus 1 factorial, that should be equal to 10 to the power of negative 6. So that if we scroll, we see that this happens at 12 point something over here. So then there's no 12 point something here because then it has to be a natural number. So then we see that beginning from 13, then you're going to get something that is smaller than 10 to the negative 6. And you can check this by just plugging it in. So if we get 2 to the 13, so if I plug in 12, let's say we want to check if this is really true. So if I plug in 12, I'm going to get 2 to the power of 13 over 13 factorial. And then if we go minus 10 to the power of negative 6, we see that we still get a positive number over here. Even though it's very small, it's a positive number, which means that this is bigger than 10 to the power of negative 6. But we want an error bound which is smaller than 10 to the power of negative 6. So in theory, this number should be negative, indicating that we are in fact smaller than 10 to the negative 6. So then what we can do is we can check, well, is 13 really the tip over point? So if I were to plug in 13 in here, so then this would become 14. This would become 14. And then we do see we get a negative number, which means in fact that if we plug in x is equal to 13, or in our original thinking, n is equal to 13, then the error we would get would in fact be smaller than 10 to the power of negative 6. So that's why all of these are wrong. Thank you. Hope this helps with the Mobius and understanding the Mobius. If you have any questions, feel free to text me or put it in the comments, and I'll be happy to answer. See you and have a great day, guys. I might be posting more videos for the upcoming quiz.